So when we approximate a function f of x with a Taylor polynomial, we typically want to know how close the approximation is. So this is given by the remainder, Rn of x, which is just the difference between the function and the Taylor polynomial. Okay, so we want to somehow estimate this remainder. So we have something called Taylor's theorem, which essentially gives a formula for this remainder. So the formula is that the remainder is equal to the n plus first derivative of f evaluated at some point c divided by n plus 1 factorial times x minus a to the n plus first power, where c is some point between x and a. So it essentially looks like the next term after the nth term in the Taylor polynomial. However, this formula is fairly complicated to work with, so we're going to try to simplify this formula a little bit, trying to give an estimate for the error. So we estimate the remainder using the following procedure. So first, choose some number m, which will bound the n plus first derivative of f for c within the interval we're interested in. So we do this if it's possible, and then once we find this number m, then the remainder can be approximated by this formula here. Okay, so let's take a look at an example. Okay, so suppose we have the function f of x equals e to the x, and we approximate it with this polynomial here. So now what we want to do is to estimate the error in this approximation. So we want to estimate it on the interval from minus 2/3 to 2/3. So we use the Taylor remainder to estimate this approximation. However, we notice this Taylor polynomial is of second degree. So 1 plus x squared over 2 is a second degree. So this is p2 of x. And so the n we're interested in is n equals 2. Okay, so we want to find the remainder. So in this case, because n equals 2, we take r2 of x. So this will be less than or equal to m times x minus a. Again, n equals 2, so this will be to the third power over 3 factorial. So furthermore, this approximation is centered at a equals 0. Because you see this is just x, which is just x, the same as x minus 0, and this is again also x minus 0. So from the form of p2 of x. So now all that's left is to find m. So what we do is we take a few derivatives of f of x. So f prime of x is equal to e to the x. The second derivative is also e to the x. so on. So you see, if you keep taking derivatives, you keep getting the same function. So f to the n plus 1 of x is still going to be e to the x over any n. So now we try to approximate this. So f to the n plus 1 of c equals e to the c. And then the interval we're interested in is from minus 2/3 to 2/3. So we just need to find m so that it's bigger than e to the c. So clearly e to the c is going to be biggest when c is equal to 2/3. But the exponential function gets even bigger if we increase c by a little bit. So this is clearly less than e to the first power. But we know that e to the first power is approximately 2.718. So let's choose an easy value for m. So this is clearly smaller than 3, so we can take m to be 3. Okay, so now that we take m equals 3, we can put everything into the remainder. So r2 of x is less than or equal to 3 times the absolute value of x, the third. So again, a is equal to 0 over 3 factorial. And again, the interval is from minus 2/3 to 2/3. And x has the biggest value at 2/3. So we'll use this. So this is less than or equal to 3 times 2/3 to the third power over 3 factorial. So let's calculate this. So we get 8 over 54, which is approximately 0.148. So within this, what this says is that within this interval, the Taylor polynomial 1 plus x squared over 2 will be at most 0.148 away from the actual value of the exponential function. But typically, when you choose even smaller values of x close to 0, this error actually will be smaller and the approximation will be better.